Alright, welcome back. Let us continue with our functions and relations slides. We're actually in an in-between state, so we need to finish these and start a new one in the same lecture. So the last thing we talked about was closure. So we learned about reflexive closure, symmetric closure, transitive closure, all these fun things. And so my first slide for today is a question for you. Please take this relation. It's a relation on just states that are numbered. 1, 2, 3, 4, 5, 6, 7, I guess. Or 1, 2, 3, 4, and 7 only. No 5 and 6, apparently. So take this, draw out the relation, and then compute the transitive closure of it. So please make the smallest relation on top of this one that is transitive. Alright, to remind us what that all means, right? If we have x related to y and y related to z, we better add in x related to z, because that jump, we need to be able to make that jump straight from here to here in a transitive relation. So we need to make sure this is transitive. Okay, so yeah, let's compute the transitive closure, and then we'll write it out as well as in this roster notation. All right, so here's our original. I'll draw in blue our original relation. Let's say this is I don't know. We have 1, 2, 3, 4, and then just 7 floating around. So maybe we'll put 7 down here. So all right, we have 3 related to 4 in that order. So 3 goes to 4 with an arrow kind of like that. Then we have 2 and 7. So I guess just come down here and do that. That was a bad looking arrow. Let's fix that. Slightly better. Then 1 related to 2. Boop. And then we also have 4 related to 3. Okay, so if we want to make this transitive, what do we have to add? Well, it's always if you have one thing and another and they meet up in the middle, you have an arrow coming in and an arrow going out, you better also have an arrow that goes all the way from the first to the last. That's what it means to be transitive. That's what it means for a relation to be transitive. So we better add in this one. Okay, that needs to be there for sure. And then I think that settles these two. That's perfect. And then these guys together, they are going to, you see how you go here and you come back? So you could have just, in one fell swoop, gone to yourself, essentially. That creates a self loop, and then so does this one. Go out, come back, they line up. So that also, to be transitive, needs to have a self loop there. All right, I hope you see that. So that, I think, is everything that we need to add to make this transitive. So what's the final relation? Well, it's of course everything you had originally. You had the 3, 4, you had the 2, 7, the 1, 2, the 4, 3. But now what are we adding? The green stuff, right? So we had to add 1 to 7. 1's related to 7 in that order. 3 is related to 3, 4 is related to 4. So these guys are the things we need to add to make the original R relation transitive. Okay? So hopefully that makes sense. Please yell at me if it does not. But I would like to now talk about things called equivalence relations, because why do we talk about all these different kinds of closures and things and transitivity, reflexivity, all that fun stuff? Well, it's culminating right here. All right? So you say that a relation R, it's called an equivalence relation, if it is all 3 of those fun ones, reflexive, symmetric, and transitive, all at the same time. All right. So you may be wondering why they call it an equivalence relation. Equality is reflexive, symmetric, and transitive, and any relation essentially that has all these 3 things, that's kind of what it means to be an equality. Right? That's kind of how equality works. So any relation that you have that is like this, it's really creating an equivalence of things. It's creating its own version of equality, because look, equality is of course reflexive there. Equality is totally, let's see, symmetric, right? If you have x equals 5, you know that 5 is equal to x. And then it's also transitive. You know that x is equal to y and y is equal to z. Of course, you also know that x is equal to z, right? Let me draw a smaller y so you can see that. But yeah, do you see how reflexive, symmetric, transitive, that's what equality is, and anything that acts like that is essentially acting like equality. So that's what it means to be an equivalence relation. And when you're working with equivalence relations, your book is saying, they use this little tilde thing here. They say A squiggle B when A is related to B and R is an equivalence relation. Okay, so that's essentially trying to say that A is equivalent to B. If this thing is called an equivalence relation, it's trying to say that it's equivalent. All right. So yeah. So the relation, you use a squiggle to mean that relation now. Every element that's linked by that squiggle, they're all equivalent to one another, right? Because it's transitive, symmetric, reflexive. And so essentially, you can talk about all the equivalent things at once. That would be nice. And you got to give it a name. And so if your relation has the domain A and you have some element in A, then you can talk about all the things that are equivalent to A under that equivalence relation, and you just put some brackets around. That's called an equivalence class. All right? The equivalence class of A. So it looks like that, and that's how you pronounce it. So it's defined to be the set of all the x's in A such that A is related to x, because it's all the things that are equivalent, right? If this is an equivalence relation, all the things that are related under the equivalence relation are therefore the equivalent things to A. All right? The set that is denoted like this is called an equivalence class for A. Okay? So essentially, like here is all these blue things. You can name them 0, or like this is number 1, number 2, element 3. These are all equivalent to one another, right? Because it's reflexive, it's symmetric. You can get to all of them. You can move around between all of them. It's transitive. You can always go there. Do you see how this little chunk right here, they're all related to one another. They're all reflexive, symmetric, and transitive. And so it's essentially like they're all one big glob. They're all one thing. They all are essentially having the same properties because they're all related to each other. So they all have the same properties. That's kind of why we call it an equivalence relation. It's acting like equality. All right, and same with these guys. These green things, 4 and 5, they're all related to each other. They're all related to each other. They're all equivalent. You see that? You can get to each of them. And then this guy by itself, 6 maybe, it is reflexive, and that's all you need to have that be equivalent to itself. It's perfect. Okay, so we can talk about the equivalence classes of all these things. It's kind of like sectioning them off into the blue things, the green things, and the red things. Yeah. So you can talk about the equivalence classes of certain elements. Like, for example, this 4 element, what is it equivalent to? You can ask for its equivalence class. What are all the things that 4 is equivalent to? Well, it's of course equivalent to itself, right? It's equivalent to itself, and it's also equivalent to 5, because you can move around as much as you'd like to get to that. Okay, so if it's an equivalence relation, this is the equivalence class for 4. It's also the same as the equivalence class for 5, right? Those give you the same set of things. They're all 5 is equivalent to 4 and 5, and 4 is equivalent to 4 and 5. Does that make sense? So yeah, like the equivalence class of 1, that's the entire set. 1, 2, 3. All the things that 1 is equivalent to. And of course it's equivalent to itself because it's reflexive. And it's an equivalence relation. And this is the same as asking for the equivalence class for 2, the equivalence class of 3. It's all the same set because they're all equivalent to each other. They're interchangeable. They're equal, essentially. All right? So I know this is very vague, but this is a cool idea and it's very powerful, especially in computer science. So, yeah. I drew these lines for a reason. When you have an equivalence relation partitions a set. Remember that term? So a partition of a set is just, it's a set of non-empty subsets that are each pairwise disjoint, so they don't share any elements, and their union is the whole thing. So pairwise disjoint again means that the sets do not overlap. Once you have an equivalence relation, you have just partitioned a set, haven't you? You've partitioned it into a bunch of equivalent things, a bunch of equivalence classes. You got the blue things, the green things, and the red things. Isn't that lovely? So that's partitions popping up again. Every partition defines an equivalence relation, essentially. And it's kind of cool in that, like, if you add more to this relation, if you like add an arrow between the greens and the blues, because it's an equivalence relation, you've just added a million more arrows, haven't you? Because it's forced to be symmetric, it's forced to be transitive, and so you've got ways to like get back to everybody and go to everybody. They're all like, once you add one arrow, everything's equivalent to everything else. Isn't that kind of cool? So yeah, they're gonna like merge together to be the same equivalence class once you do that. So that's That's what it means to be an equivalence relation. They define partitions, they have equivalence classes, all the things that are equivalent to each other under that equivalence relation. So with that, I would like you to try this. This is definitely a harder question, but it's a really fun question to answer once you get it right. So see if you can figure out if this relation is an equivalence relation. We're saying that x is related to y if, it's a relation on numbers, if x minus y is equal to 3 times m for some integer m. So let's say that this is a relation on integers. All right, and this is true, they're related, two integers are related if this is true about them. See if that's an equivalence relation, please. All right, so remember what it means to be an equivalence relation. It's got to be reflexive, symmetric, and transitive at the same time, so we better check all of those. It better be reflexive, it better be symmetric, it better be transitive, all at the same time. So let's figure this out. Let's try some examples. Or actually, it's easy to try some examples first. Like, what are some elements that are related under this relation? Let's see. If subtracting them is equal to 3 times an integer, positive or negative. So it's like they're off by 3, maybe like 6 for example. 6 is related to 3 under the relation R, right? Because 6 minus 3 is equal to 3 times 1, and m can be 1 there. Does that make sense? What else? 9 is related to 6 along those lines, right? It's still 3 times 1. You can go even further. You can be like 9 is related to 3, right? Because that's equal to 9 minus 3 is 6, which is 3 times 2, right? And so you can go on, and m can be negative as well. It's fine. It's happy. So that's kind of what the relation looks like. That hopefully gives us some intuition. Let's see what else. What do we got here? And yeah, you could keep going. You could ask, like, all right, there's a bunch of different integer m's. Like, what does it look like when m is 0? What are the things that are related when m is 0? It's like when x minus y is equal to 3 times 0. That's saying that everything's kind of related to itself. Ooh, right? Because reflexivity is when x is related to x. Do you see how? If you set m to 0, 1 is related to 1 because 1 minus 1 is equal to 3 times 0, right? 2 is related to 2. 3 is related to 3. So every number, it really is related to itself. Do you see that? This is a reflexive relation. Does that make sense? Because, like, it's just like x related to x is always true, right? Because x minus x. Is x related to x always true? Yeah, because x minus x is equal to, it's got to be equal to 3 times m, but it's just like, is 0 equal to 3 times m? Well, yeah, if m is 0. That's perfect, because 0 is equal to 3 times 0. So do you see how this is a reflexive relation? That checks out. That's perfect. So this is totally a reflexive relation. What about, like, m equals 1? These were some examples with m equals 1, kind of, right? That means they're kind of off. Like 6 and 3 are related under this relation. 9 and 6 are related. It helps to draw out these examples. 4 and 1 are technically related, right? It doesn't have to be multiples of 3. Just their subtraction needs to be a multiple of 3. M equals 2. These are like 6 and 0, 7 and 1, 8 and 2. Do you kind of see where I'm going with that? These are all equal to 3 times 2, right? Their subtraction is equal to 6. So, all right, this will help us, right? Now some examples helps us. So now let's try and prove if it's a symmetric relation. Is x related to y? If it is, if x is related to y, is it also true that y is related to x? So let's see. Kind of haven't given you that example yet. But technically, what do we got? I think that is true, right? Because if 9 is related to 3, for example, do you see how, like, 3 is totally related to 9, because 3 minus 9 is just negative 6, and that's just 3 times negative 2. So I think that it's always going to work out. So I think that will be fine. Let me see how I can prove that to you. If I have that, all right, if I know that x is related to y, if I have this, I need to prove that y is also related to x. So, all right, if I have that x is related to y, that means x minus y is equal to 3 times m. You could spell this out a bit more, but this is the idea. Is it also true that y is related to x? Because I need to show that y minus x, right? I need to show that y y is related to x in that order. So then y minus x better also be equal to 3 times something else. 3 times, I don't know, m prime, I don't know, something like that. But do you see how, like, if you know this, you could totally get this. You could totally find an m prime. It's just the inverse, or the negated version of the original m. Because if this is true, if you just multiply both of these sides by -1, do you see how you get y minus x on this side equal to 3 times negative m, right? Negative the original m. Negative the original m. So that is another integer, and that will work out. That's saying that y and x are related if you had x and y related. So that's the flip side. That's the other side of that. That's going to give you symmetricity. Isn't that lovely? So that's my proof. It's essentially a direct proof. It's like if you have this, then you have that. You see that? I just proved that in a kind of hand wavy way, but hopefully you see that. You did kind of a direct proof. So that checks out. It's symmetric. Now we need to see if it's transitive. Is it transitive? Well, that means if I have that x is related to y, right? X is related to y means that, all right, I know that x minus y is equal to 3 times m. Let's just be like m1. And if I know that y is related to z, that means I know that y minus z is equal to 3 times m2. I need to show that x is related to z, right? Which would be showing that x minus z is equal to 3 times some m3? Question mark? Does that work? Is that always true? Can I always find an m3? Let's try. Let's use some math and see what's happening. All right. If I have this, if I have these two, do you see how I could add together both equations? I could add together both of these sides and add together both of these sides. And that will give me x minus y plus y minus z equal to 3m1 plus 3m2. Yeah. And then the y's are going to cancel, minus y plus y. And that leaves me with x minus z equal to, and then I can also bring out a 3 here. Ooh, 3 times m1 plus m2. So there's my value for m3. I could use that. Let me draw this a little bit tighter so that I can fit it all on the slide, but you get the idea. m2, and that could be my value for m3. I found an integer that shows that x is related to z. If I had that x was related to y and y was related to z, I got the third thing. You see that? So that proves, again, it's a hand-wavy proof. You'd have to spell it out a little bit more, but all the good pieces were there. I said them all. But that's showing that it is also transitive. Do you see that? Isn't that lovely? So this is an equivalence relation. It's saying that if this is true about some elements, that means they're related under some sort of equivalence relation. Do you see which one it is? Like, what's equivalent about these numbers? Like, what's so true about them? 6 and 3, 9, 6, 4 and 1, they're equivalent to each other. 6 and 0, 7 and 1, 8 and 2 are equivalent to each other. What's it saying here? What's it doing? Well, if you think about it long enough, it's essentially doing an equivalence relation on using like modular arithmetic. All right, it's essentially doing a mod 3 equivalence relation. And let me prove that to you. Because what are the equivalence classes? Equivalence relation. What are the equivalence classes? Like 0, like what are all the things equivalent to 0 under mod 3? 0, 3, 6, all these things are equivalent to 3, right? To 0. 9 is related to 0, is related to 3, is related to 6, because they're all offset by a factor of 3. Do you see that? 9, 12, 15, 18, those are all equivalent to each other. Run it through the relation. Do you see that? They're all related to each other. So that's an equivalence class. All the things equivalent to 0, and then everything equivalent to 1, right? 4 and 1. 1, 4, 7. These are all equivalent to 1, right? Because they're all the same mod 3. Isn't that so cool? And then the last equivalence class, of course, is like 2 is equivalent to 5 is equivalent to 8. ... These are all your equivalent. These are your 3 different equivalence classes. Little clouds, little partitions of the integers. And of course the negative numbers are here too. But this is hopefully making enough sense. So this is the relation that defines essentially mod 3. Do you see it? So it's definitely a harder question. Hopefully you figured out that at least was reflexive, symmetric, and transitive. See how I'm proving that. But that's kind of cool to notice, like that's how you would define what it means for numbers to be equivalent mod 3. That's how you define the equivalence relation on them. All right, before we go, finishing up these slides, the last thing I want to talk about is n-ary relations. So this is when you relate multiple things, a bunch of things at once. So we've been relating just two things, like this x is related to y, y is related to z, etc. But you can have a relation on a bunch of things at once. Like we were working like this, like x is related to y, z is related to w. You could also say that a bunch of things are related at once. You can be like x, y, z, w in that order. They all share some. Some relationship holds for all of them. And then like p, q, r, s, some relationship holds for all of them, and we can define that relationship where you need to input more than just two things, right? So this is saying that we have a relation on a bunch of sets, like a1 through an, where those are our n elements of these kinds of tuples, all right? What does it mean then to define a relation on a bunch of things at once? It's really just, well, just give a 4 tuple to represent that. So it's a subset of a Cartesian product, a bigger Cartesian product, and we call it an n-ary relation when there's n things, right? Trying to be general. This is like a 4-ary relation, elements of that, perhaps. And so, yeah, that's pretty nice. Let's see, what else could I do? One thing that n-ary relations are good for is computers, computer science, modeling programs. So let's see, what was I going to do here? What lecture are we in? So I'm not going to give you any code, really, but I'm going to have you think about code right now. Because what can you do? You can model the input and the output of functions as relations. If you're allowed to use a bunch of stuff like this, you have extra elements, functions, and programs themselves as n-ary relations. So for example, in Racket, there's an append function on lists. It takes two lists, 1, 2, 3, 4, 5, 6, and it brings them together to make one big list. It appends them in that order, so it creates this list. So you can define a relation to talk about in math what append is doing, and then maybe you can prove stuff about it. So we can define an append relation where it's defined like this. Append is the relation on three things, the following. It is x's and y's and z's. It's these three things in that order, where x, y, and z are lists, and the first two lists appended together is equal to the last one. Append on x and y is equal to z. So do you see how this is representing in math, essentially, what is going on with the append function? So you can now prove stuff about append. What are elements of this relation? Well, the list 1, 2 and the list 2, 3 are related in the append relation to the last thing. It's kind of an input-output thing, right? 1, 2, 2, 3. So this would be an element of the relation, the append relation, saying that these two things append to be that. So we're defining kind of how append works in math. What's another element of this append relation? Like the list with just 1 in it, and the list with just 42 in it. These are all related to the list 1 and 42, right? One big thing. These three elements are related in the append way, right? Where this list appended to this one is that. So you can define input-output relations, essentially, on any computer program in math now. Isn't that lovely? So that's very powerful, very cool. We'll talk about that soon, but that's kind of a starting point about proving properties of programs. It's pretty nice. So here's my last question for you. Here is a n-ary relation, a 4-ary relation, I guess, on integers. So I would like you to express the following relation as a set of n tuples in roster format. So tell me that R is equal to, and then list out every single element of the relation R. All right? But here it is defined in set builder notation. Just list every element out. Try to figure out them all. So here is the relation R. A, B, C, and D, they're all related to each other if they are all positive integers, and then also A plus B plus C plus D is equal to 6. All right? So this is defining the relation. See if you can spell out exactly, hard code, all of the elements of this relation. What are all those elements in this relation? Okay, so let's list them out, I guess. keep it easy on ourselves, these are all positive integers. Like a could be 1. The first numbers for a, b, and c would be like 1, and then d would be forced to be what to make it 6? Be forced to be 3, right? And so you can spell them out in this way: 1, 1. If this, then you could make this one 2, and then what would this one be forced to be to make it all 6? It would also have to be 2, right? So then we could do 1, 1, 3. And then we have 4, so we need, we have 5, so we need just one more. And so those are all the ones where it's like 1, 1 something. And now we can do 1, 2 stuff. 1, 2, 1. What is this one forced to be? So that's 3, 4, 2. And so you can just spell them all out. 1, 2, 2, 1. Just all these things where it's equal to 6. Do you see it? So these are all, you can define any kind of relation you want. This is just a relation on positive numbers where all of the pieces summed together, they form to be 6. 2, 1, 2, 1. And these are like different from each other, right? Because these are tuples. These are tuples, and so order matters, even if they have the same elements. 2, 2, 1, 1. And then I think the last one would be 3. And then you're forced to put a 1 in every other place. You could also totally write a program to find all these, and that may have been what I did before. But that's the idea. Okay? So, let's see. Is that what I wanted to say here? I think so. So yeah, that is as much as I want to say for now on functions and relations. These are very, very important things. They'll be coming back to us throughout the rest of the class, most likely. So that's a good start, though, on them. And so with the rest of our time today, I'd like to talk about algorithm analysis. Woohoo! So this is going to take us a while to get through. There's a lot to talk about. We're finally like tying it all back to computer science in a very, very fun way. So yeah, let's talk about algorithms, because we're going to analyze them in a way that is very similar to what we learned in CSCI 41. We're just going to hit it harder with math this time. Okay? So what is an algorithm? But it's just like a recipe, right? It's a step-by-step way to create an answer to a problem. Step-by-step method for solving a problem. It's just a recipe, because like if you've ever modified a recipe, you've essentially programmed in real life. Flour plus milk plus eggs plus like baking soda, blah, blah, blah. That'll give you pancakes, for example. An algorithm is just a recipe for something that you want, a computation that you want. And so our goal for this class is to learn some cool math that will help us program better. And so if we would like to formally reason about our programs and argue that they are correct beyond any shadow of a doubt, then we have to list down, we have to formalize how code gets run. We have to talk about, let's say that we're going to program our algorithms on paper in pseudocode. We have to talk about every kind of line of pseudocode and what it means, right? And so let's make it easy on ourselves for right now. Let's just pretend we're not going to allow functions. Like, you'd have to list all the code out. So if we don't allow functions, then the current state of our program, in between lines, for example, is essentially represented by the values of all the variables involved. So here's an assignment. Assignments look like this in pseudocode, like x gets the value y, something like that. So let's be like x gets 4. That's like a line of pseudocode. And then here's another line of pseudocode. X gets x plus 1. Okay? And so essentially there's a state of a program. The state of this program, you can follow it. You can track it by mapping the values of the variables, right? And so every time you make an assignment, it's changing the state. It's changing the value of one variable. It's like taking whatever was on the left side and changing it into whatever the value of the right side computed to be. So for example, like if the let's say like the old state before this line got run was like old state was that x held 42 and y held 7, for example. Then what's the new state after this line gets run? What's the new state? Do you see how you could list it out? You could enumerate it. You could formalize it. Well, x is still 42. We didn't touch x with that line, but this is, oh, sorry, excuse me. We did touch x. Y is still 7. We didn't touch y with that line, but we totally messed with x. We set it to whatever y was, and y apparently was 7. All right, so x is changing to be 7, and y didn't get messed with. Y is still 7. Okay, so that's how that works. And so let's kind of do that for this. Here's like a two-liner, line 1, line 2, pseudocode program. Let's say that this is the start of the program, so the state looks like emptiness at the start of the program. And then in between every line, you can draw the new state, like what happened. This helps us formalize what happens about our program. So like beyond a shadow of a doubt, what does the program look like right now in between these lines? Well, x holds 4. See that? And then you can prove then. You can mathematically prove now that we're doing this. What does the state look like now? After that last line, well, x was 4. Well, now we're setting x to be the old x plus 1. If the old x was 4, we can show and prove that x is now 5. Do you see that? That's how you prove that your programs are correct. This is essentially a proof that this program results in an x variable holding 5. And this totally generalizes. It generalizes to cooler things. All right, so let's talk about all the different ways that you can program in pseudocode. Let's talk about if and if else. So like an if statement, for example, what's it going to do? How does it run? It checks its condition, and if it's true, it runs the body. If else's, also check the condition, run the body, the true branch if it's true, false branch if it's false. So you can reason about it mathematically by like realizing what it's doing. If statements, they look at their condition first, and then they go down one path or another, right? They execute the true branch if it evaluates to true, and the false branch if it evaluates to false. So for this one, for example, how would you formalize what's happening when that's running? First, you're going to check the condition. You're going to check it, test it. Test that condition, see if it's true or false. If it's true, you'll go down and you'll execute the body of the if, the true branch. Execute the body of, let's say, the if side, the if branch. And then if it was false, you're going to execute the body of the else. All right? And then it comes back once it's all done, like you go back to the rest of the program. Rest of program. I hope you see that. So yeah, that's essentially how this is working. You can spell it out like that. That's how ifs and if else's work. Whiles, that's your most general loop, right? How do we formalize what it means for a while loop to run? Well, again, it's going to run its condition, and the body, it's just going to repeat that, right? Repeatedly executes its body as long as the condition is true. So we can model that, like you're coming into the while loop. It's always going to check the condition first. And as long as it's true, it'll run the body of that loop as big as it needs to be, and then it always comes back and checks the condition. It'll keep looping like that. That's what it means to be a while loop, right? The second that condition is false, though, the while loop stops, and so then it goes back down to the rest of the code once that's false. Rest of code. Okay? And so that's how while loops work. Here's one thing that you can immediately prove, right? If a loop ever stops, if you get to the rest of the code, that means the condition must have been false. You see that? Have you ever considered that when you were writing your code? Maybe. Maybe even subconsciously. But now, think about it. Like, that is beyond a shadow of a doubt. The condition must have evaluated false for me to get to the code after the while loop. You see that? Isn't that fun? Your book also talks about for loops, but you can always translate a for loop into a while loop, so I'm not going to spend time on them here. But isn't that fun? We're now formally reasoning about our programs. If you can write down this kind of stuff, you can prove that programs are correct. Okay? So I also want you to just get practice writing not C++, so that's why I'm teaching you Racket a little bit. But here, try pseudocode. Write an algorithm in pseudocode for the following program. Description of input and output. So you are going to get two pieces of input. You're going to get a sequence of numbers, say like as an array or a vector, pretend, where n is bigger than or equal to 1, so you're always getting at least one thing. Sequence is not empty. And then n is the length of the sequence. So you're getting the array and the size of the array, let's say. And then your output, your algorithm that I want you to come up with, needs to do this. Output true if there are any two separate numbers in the sequence whose sum is 0, and false otherwise. All right? Give this a try. See output true if you can find two numbers in this sequence whose sum is 0, and false otherwise. So here are some examples, input-output examples. So like if the input sequence was like 1, 2, 3, and the size, of course, is 3 there, you're going to output, you're going to say false because you can't, there's no two numbers here that you can sum together that would give you 0. Okay, see that? So there's that. And then this one, 1 to -1. You see how that one, like size 3 again, that would output true for sure, because you can take the 1 and the -1, sum them up to get 0. So that's, if you have any of those, you find like the mirror image of a number, it's negation somewhere, then you can say true. All right, so give that a try. Maybe I just gave away one of the answers, but there's more than one answer. There's like a fancy way that involves only linear time, scanning through the sequence once. See if you can find it. All right, so like the naive way, the way that maybe you're thinking of is like, all right, I need to find two numbers, so let's just iterate twice through this thing. Let's iterate twice through the thing. You'll be like, all right, for I equals, this is pseudocode for loop, I guess, for I equals 1 to n, and then for j equals 1 to n as well. And then we're going to check, right? Now we have AI and we have AJ. We can look at both of them and see if they add to 0, right? They're supposed to be different elements, though. So technically, like if it was just a single 0, you can't just like add it to itself or anything. That's not allowed. It's got to be two separate numbers. Two separate numbers. They can't be the same indices, so we'll have to watch out for that. But here's our sequence. We can index into it. This is like A of I, A of j. So if AI plus AJ is equal to 0, and I is not equal to j, they need to be separate elements, right? Then what we'll do is we'll return true, because we found two elements that are different that add together to be 0. And then otherwise, if we stop this entire loop, get down here, the outermost, it's done, then we'll return false, because if we got here, that means we never returned true. We never found two numbers. See that? So that's the idea. Dun dun dun. You could do this a bit faster. There's one way to make it faster, because you see how like if you tried I equals 1 and j equals 3, so this would work. First of all, even before I get into this is gonna work. It's fine. It's n squared, right? You see that it's n squared, going through n twice. You're trying a bunch of stuff. So you could make it a better n squared by doing this. You'd be like, if I is 1 and j is 3, do you see how you're like duplicating effort? Like you're gonna test then a of 1 plus a of 3, but then you're also going to later, right? If you haven't found anything yet, you're also gonna have I set to 3 and j set to 1. You see that? And then you're gonna test a of 3 plus a of 1, but you've really already tested that. So that's duplicated work. So there's a few ways to solve that problem. Let's see, how do I want to say this? Dun, dun, dun. Yeah, so let me solve that for you. It's still going to be n squared, but it's going to be a better constant out in front of the n squared. So here's how you can force it to just be like, essentially you can be like, don't ever flip it like this. Don't ever come back around, because you see how this index is bigger than this index. Let's just like always work when I is less than j, because then we would never retry things. So let's do it that way. So we can change this into for I equals 1 to n, and then for j equals, we're always going to make sure that j is bigger than I, so that we don't ever wrap back around and do the other side, because it was unnecessary. For j equals I plus 1 to n. See how that'll also work? And then now, if ai plus aj is equal to 0, then we don't even need, right? We don't even need the and I not equal to j, because it's guaranteed to not be equal, because j starts out as being I plus 1 always. It's never going to be equal to I. So we don't even need this. So I'll use like green. Say like we don't even need that now. So fewer checks as well. It's better. Beautiful. Then we'll return true. And then otherwise we'll return false again. I guess I want capital things, and that R looks weird, so let me fix that. Return false. So yeah, now always I is strictly less than j. We've guaranteed that I is strictly less than j so that we can never wrap back around and retry things. Isn't that lovely? So I is less than j now, always. And so that means we're trying fewer elements, but still, if you do the analysis, do you see that still n squared? So this is something from, this is like CSCI 41 stuff. I assume you know how to analyze this algorithm. So this is like I going from 1 to n, that's definitely going to loop n times in the worst case. About n times, more or less. It's going to run its body n times in the worst case. This one is also going to, well, it's going to run its body n minus 1. The first time when I is 1, it's going to run the body n minus 1 times. Then the next time when I is 2, it's going to run it n minus 2 times, n minus 3, n minus 4, n minus 5 times, all the way down to just 1 time at the very end. So if you spell it out, it's really going to end up being about n times as well. There's an analysis there. But really, essentially, it's doing it n times as well in the long run. So in the worst case, this is still n squared, but it's a better n squared than this one. Right? Do you see that algorithm? So there is a linear time solution if you trade some space for time. If you make a hash table and you store things that you've seen before, do you see how, if you just read through the sequence once, the second you get to -1, just go looking for +1, because that's the one that would add to make it 0. Go looking for +1 in your hash table, you'll see that it was already there. In your set, maybe. It's like stored as a set of things. Isn't that lovely? So that would be, because hash tables take linear time to look up, or hash sets, I guess. You can use unordered set in C++. Then you'd find the thing in constant time for each iteration, and you'd only have to go through the sequence once. So that's kind of cool to think about. Ask me more if you're curious. But where we're going with this is like we are hitting hard this sort of algorithm analysis, right? I assume you know how to do this, but we are going to do it better now in this class. We're going to learn exactly why it works. Like, why do we say big O? Like, what does that even mean, really? So that's where we're about to go. So our goal, what big O analysis is we're talking about essentially the growth of a function. The asymptotic growth of a function. Remember what asymptotes are? It's like you have some sort of function that you create in math, and like it's never going to get bigger than this. Like you're bounding it somehow. That's kind of what we're doing with big O. So that's what it means for asymptotic growth. The asymptotic growth of a function, call it f, is to measure how fast the output f of n grows as the input gets bigger. Input n grows. So again, asymptotes, they just bound things. It's like these dotted lines in math. And then we would like essentially an accurate bound for our function f. And our function f is kind of mapping how much time it takes or how much space it takes for our algorithm to run. Okay? Usually you don't care really exactly how fast a function grows. We'd like to just approximate it, all right, in a good enough way. There's like an infinite amount of different yet similar ways to write a function, and like both of these are n squared, right? There's not a huge difference between their running time as n gets large. That's kind of how those mean. That's kind of what we're talking about. Essentially, we want to put both of these functions into the same O of n squared equivalence class. Ooh, I'm using that word again. So that's kind of where we're going, all right? So we use big O. There's also big omega and big theta to talk about different kinds of asymptotic growth, and I'll pronounce them again. This is big O. We say that as big O, big omega, and big theta. Technically, this is also a Greek letter. It's like big omicron, but everybody just shortens it to, we think that it's a Latin letter now, but it's really a Greek letter. So yeah, essentially we're going to create mathematical functions that model how fast our algorithms grow in terms of time or space, usually. Okay, so we can use functions to bound other functions. That's where we're going. So we can make one function that bounds our other kind of cool function that's a little bit more complicated. So it's like we've got this function, but we can use this other function to bound it, right? You see that? We have this function maybe right here, but we can use this other function right here to bound it. You see how it's always bigger? That's essentially what it means to be big O. Like this function above is bounding the one below. This function above is bounding the one below. That's kind of what big O means, all right? And so I have these other ones too to tell you about, and we'll get there later if you haven't heard of them before. But that is where I want to stop right now, and then we'll come back and talk a little bit more about algorithms and their analysis.